So we're kicking off the second part of chapter 5, and we're going to be discussing rational functions. So the first thing we're looking at is the domain of these two functions. What would the domain be of g of x, capital G of x? Biggie? Good. And x cannot equal -3 or 4y. Letitia? Good. Because the denominator cannot equal 0. Nice job. Now, did anyone factor the denominator for f of x, capital F? Now, what you got?
2x plus 1 times x minus 3.
Okay. And what was the resulting domain given that factor denominator? Emily?
All numbers except -half and 3.
Okay. Any questions on capital F of x domain? So you'll notice that a rational function does not have a domain of all real numbers. So what this means is that the graphs of rational functions will look different than the graphs of polynomial functions. Polynomial functions domains are all real numbers, so there's no breaks in the graph. But this will have breaks in the graph because there are domain restrictions. So today we're going to get a sense of, number one, what those domain restrictions look like on a graph, what the graphs look like, and some other features of those graphs. So the definition of a rational function, just to remind you of it, is it is the ratio of two polynomial functions, p of x over q of x. The only restriction is that q of x can't be 0 because we can't divide by 0. The domain, we figure it out by basically saying it can be any real number except numbers that make the denominator 0. And that's what we utilize to find the domain of those rational functions for our entry problem. Any questions? Now, rational functions are unique from other functions we have studied in that they have what are called asymptotes. Now, asymptotes are lines that cut through the function. They're imaginary, you don't see them, but you draw them using dotted lines in order to guide the graphing of the function. It's a Greek word, meaning not falling together, but essentially, it's either a line that the curve will never cross, or it's a line that the function approaches as end behavior. So two different types of asymptotes in terms of two different categories that we're going to learn about today. And when you say the word asymptote, make sure you're saying the word tote, like a tote bag, not tote, T-O-P-E, like an isotope. So we're saying tote, like a tote bag, asymptote. Okay, so here are the three different asymptotes. Just so you know, this is kind of an impossible graph because the blue and the red asymptote would never occur on one single function. So I have kind of manufactured this for you. So we have a horizontal asymptote here, that's the red, a oblique asymptote, which is the blue, and a vertical asymptote, which is the green. And we're going to learn how to find these today. And then moving forward, we're going to learn how to graph these functions. And so oblique is just another word for slanted. So all of these are linear equations. Two of them are functions. We know that the vertical one is not a function. And so the red and the blue describe end behavior. Okay, notice what's happening at the ends of the function. Whereas green is a do not cross line. And so that's what this says. Vertical asymptotes are complete breaks in your graphs. In other words, it is a do not cross line. You never cross a vertical asymptote. whereas horizontal and oblique asymptotes describe the end behavior of a graph. So when we learned about polynomials, end behavior was either up or down. Those are the only choices. But now we get new categories of end behavior. Horizontal means end behavior is just flat, just goes flat, out left and right. Oblique means it goes along a linear equation, like y equals x. It could go along obliquely, or really any linear equation of a line. So this gives us other options for end behavior besides just going up to infinity or down to negative infinity. And that's what asymptotes do, is they either provide do not cross lines or they describe the end behavior of the graph. Any questions on that? All right, so these are actual graphs that can occur. On the left, we have two different types of asymptotes. Can somebody identify the asymptotes which are on the graph on the left? Do we have oblique, vertical, or horizontal? Andrew, what do we have?
There's one vertical and one oblique.
Okay, yeah, we have a vertical. Andrew, what's the equation of that vertical asymptote? X equals what?
-1, or -1/2.
Cool. And then the oblique, again, oblique is kind of just another way to say slanted. We could write the equation of that line if we wanted. Normally, we just find the equation and then we graph it. Very rarely would you have to go backwards here. So this one has an oblique asymptote. Notice it describes end behavior. The ends of this function are hugging this asymptote. Now, you can cross oblique asymptotes, that's fine, whereas you cannot cross vertical asymptotes. Vertical asymptotes cut the curve into two separate, what are called branches. So because this graph can never equal -1/2, it has a vertical asymptote that cuts it. So you cannot cross this line, x equals -1/2. What kind of asymptotes are on this graph on the right? What do we have here? Letitia?
You have two one horizontal and two vertical.
Okay, what are the equations? We have a horizontal, and what's the equation of the horizontal asymptote?
Y equals 1.
Cool, yeah. And then what are the vertical asymptote equations? Okay, and? What's that? Any other vertical asymptotes? 8? Yep. And the reason we know there has to be another one is there's 3 branches. If there's 3 branches, it's like it has to be cut twice. You see how it's like right down here? So I think they didn't draw it because it's right on top of that y-axis. But it's there because we have those 3 branches. So 3 branches would indicate 2 different vertical asymptotes. So again, vertical asymptotes you cannot cross. Horizontal asymptotes you can cross. Notice this middle branch is crossing the horizontal asymptote right here, but it describes the end behavior. Notice I'm hugging that horizontal asymptote right here as I go up to positive and negative infinity. Okay, and we're going to learn how to graph these. They're kind of, in my mind, the hardest things that we learned to graph. Like, I really couldn't believe that we did this in this class when I first started teaching it. But you'll get good at it, I promise. Okay, so there are 2 different things that can happen when you have values that make a denominator 0. Either you get a vertical asymptote or you get what's called a hole in the graph. So let me give you an example. Let's say you had y equals x plus 1 over x minus 2 times x minus 1. We can see we're going to have two domain restrictions. X cannot equal 2 and x cannot equal 1. So we're going to have two vertical asymptotes. They're going to be at those spots, x equals 2 and at x equals 1. So those are the two spots that are going to cut vertically through your curve. So vertical asymptotes occur when you have non-cancelable factors in the denominator. Let me say it this way. Non-cancelable domain restrictions. None of these canceled out. Whereas a hole can occur if you have cancelable domain restrictions. So for example, y equals x plus 1 over x minus 2 times x plus 1. So here we would have a hole at x equals -1, and we would have a vertical asymptote at x equals 2. So if one of those factors cancel out, it's still a domain restriction. It's still, I still say x cannot equal -1, even though it cancels. But it doesn't provide you with a vertical asymptote. It just provides you with a little itty bitty tiny hole in the graph. It is so, it's kind of fun when you've got a hole in the graph because it's very small. And essentially what it looks like, this graph would kind of look like this. Just give you a sense. At 2, I would have an asymptote. And you won't know how to graph this yet, so just follow along. This isn't something you know how to do quite yet. You would actually have an asymptote right here. And it looks something like this. And it says I have a hole at -1. So actually what you would do is go to -1, x equals -1, and go to the graph, and you make a tiny hole. Like a little hole. You'd erase, and if I erase, it would be huge because you guys know how big the smartboard eraser is. And it's just like a tiny hole. It's really cute though. I kind of want to show you on the graphing calculator. Can you, you have this on your paper? Grab your graphing calculators. So if you were to graph, and the way you graph these is you really need to use parentheses. Our numerator was x plus 1, so parenthesis x plus 1. Your denominator was parenthesis x minus 2, yeah? Or was it x plus 2? X minus 2, parenthesis, and then x plus 1. And that parenthesis. So you have to put the whole shebang in the parentheses in the denominator, or it's going to mess up. So that's why I need the double parenthesis in the denominator. So it divides by both x minus 2 and x plus both things. Now, if you hit graph, we said we were going to have a hole at x equals -1. Okay, so clearly my zoom is crazy, so I'm going to hit zoom 6, and there it is. Now, do you see a hole at -1? So watch this. I'm going to hit zoom in, so that's zoom 2. And I'm going to go to -1. So I'm going to, you guys see how I have this little plus? So I'm going to put it right on top of x equals, oh, is it at +1 or -1 the whole? Okay, so let me go over here, -1. Right on top of my graph. Enter. Zoom in. And now I'm going to zoom in again. Enter. Enter. Oh my gosh. Come on, baby. Enter. Enter. Oh my gosh, come on! This will be so anticlimactic. You're not going to believe me. All right, I'm going to have to zoom 6. I'm going to show you in a different way because this calculator might be punking me right now. Okay, so go to the table, second table. Look at the -1. You see that says error? Yeah, it's telling you it's a hole right there. The calculator should put a little space. Should be a little, boop, little mini hole. But it's being a bit of a punk. It doesn't want to put the -1 little hole there. Oh man, let me change my window. Let me just see. If I'm going between -2 and a window of 0, oh man.
It's not showing to me at all.
Yeah, I think it's the operating system.
Wait, everything can do or only it.
Look! I promise! It's here! Do you see it?
Why does it only work sometimes?
Well, okay. Okay, change your window. Here you go. It should always work. It's just the calculator doesn't love holes. It's trying to fill in all the gaps. But it should have a gap at -1. It just needs to be zoomed properly so you can see it. Yep.
No.
Don't do that. Just do the window, because did it not work with the window? It worked? Okay. Yeah. So here it is. It's a little boop.
How would we graph that like on a test? You just erase it.
Young man. Oh, on a test, yeah. So basically, if you're graphing it and it's going along, you go like this. You exaggerate it. Because if you wouldn't exaggerate it, I wouldn't see it. But yeah, there's an actual hole. It skips over at x equals -1, which is actually really cool. I mean, relatively speaking. Are you not getting it, Andrew? No? Okay.
How do you do it? You press zoom and then press zoom in.
I believe in you.
All right. Your window is a little off. Okay, let's take a look at this screen. This is how you determine, so we learned that we determine whether you have a vertical asymptote by looking at the denominator and looking at the domain restrictions. If you have a domain restriction that doesn't cancel, you will have a vertical asymptote. Okay? To find whether you have a horizontal or oblique asymptote, you can follow this flow chart. Now, the reason that you have two copies of it, one in the guided notes and one on the half sheet, is because this half sheet is so valuable. I have students in pre-calc and in calc coming back to ask me for it. It's like really cool. So it's a little more handy than that whole big packet that you might want to put in a binder. But this you can have, just ready at the ready when you need it. Now, my hope is that you don't need it once we learn a little more about rational functions. But while we're learning, you can use it. If you don't write on it, you can use it on the test. And so this tells you how to find horizontal and oblique asymptotes. So let's take a look at this. It says find the horizontal asymptotes if any of this graph. Now, if we go back to this, this has you determine whether you have an oblique or a horizontal asymptote, making sure to pay attention to the degree of the numerator and the denominator. So looking at the flow chart, what kind of asymptote would we have? And I want you to take a look at the flow chart and tell me if you'd be on the red, the blue, or the green side of the flow chart. Which one? What degree is higher? So yeah, you'd be on the green. So where's your horizontal asymptote? Yes, at y equals 0. So it says if the numerator's degree is less than the degree of the denominator, you will have a horizontal asymptote at y equals 0. So just following the flow chart. Now I'm going to explain why this is true. Now horizontal and oblique asymptotes are all about end behavior. End behavior is all about thinking about as x goes to infinity. Now as x goes to infinity, think as x goes to infinity. Will the negative, the minus 12 be important? No, x is going to infinity. X is million, x is billion. We're thinking Jeff Bezos dropping $12. Meh, doesn't really matter, right? This becomes negligible. Now look at the denominator. We have 4x squared plus x plus 1. What becomes negligible in the denominator? The 1. Anything else? In terms of terms. Actually, the x also becomes negligible. Because once you start to square things, they become absolutely huge compared to things you don't square. So we have dominating terms in our numerator and our denominator, okay? And those are the lead terms. So this is approximately x over 4x squared, which is 1 over 4x. Now, as x goes to infinity, what does this get really close to?
0.
0. Because this is like 1 over a really big number. 1 over a really big number, like 1 100, 1 1000, 1 1,000,000. That's very, very close to 0. So that's why the horizontal asymptote is at 0. Okay? And if it doesn't click in, you have the flow chart. Okay. So let's look at the next one. Find the horizontal or oblique asymptote of this graph. Take a look, where are we on the flow chart? Blue, red, or green? Blue. So it says, do polynomial long division. Let's do it. This is not a nice one. I'm trying to add some zeros just to spread it out a little bit. I don't know if I'll need them, but we'll see. Okay, so x cubed times what is 3x to the 4th? 3x, good. And then below I'll write the product of 3x in my divisor. Subtracting, these cancel. I get 3x cubed minus x squared minus 3x. Any questions on that move? Okay, x cubed times what is 3x squared? 3x cubed. 3, yeah. And then I multiply. And I subtract. Now the beauty of this is we don't really care about the remainder. Because all we're doing, if you read down the flow chart, is it says if the quotient is linear, you have an oblique asymptote. Is the quotient linear? So is the result from dividing linear? So is this linear? 3x plus 3, is that linear? Yep, so that means we have an oblique asymptote, and this is the equation. So the equation of our oblique asymptote is y equals 3x plus 3. And the remainder just basically goes to 0. It doesn't make a big difference. So that means if you think of the line y equals 3x plus 3, it's a linear equation, something like this. That describes the end behavior of the graph. So the ends of your graph are going to be up on this side and down on this side with a slope of about 3. So when they say oblique asymptote, they're basically giving you the equation of the end behavior. Questions on that? What do we think about this? Red, yeah. The numerator's degree and the denominator's degree are equal. In that case, find the ratio of the lead terms. Here are the lead terms. What's the ratio of those terms? 2. So yeah, it's just y equals 2. It's a horizontal asymptote. The best case scenario is it's not the blue one. The least amount of work. And just to go through the exercise, like why this is true, is when we're looking at x going to infinity, there are terms that become negligible. Okay, remember, we're thinking glucose bucks, x is at 1 million, 1 billion, 1 trillion. The 8x squared dominates the numerator. So this becomes negligible, the minus x, and the 2 becomes negligible as x goes to infinity. Squaring things makes them so much bigger compared to just x compared to the 2. And the denominator, minus 1, becomes negligible. So as x goes to infinity, this is approximately 8x squared over 4x squared. So it's approximately 2. Okay. So we're thinking all about, like, basically squinting as this. As x goes to infinity, things become less important and other things become more important. And it's those lead terms that become more important as x goes to infinity. Questions on that? Now let's look at this function. Where are we on our flow chart with this rational function? Yeah, we're at the blue, so we're going to do some polynomial long division. Good thing we just did a little bit of this. So x cubed times what is 2x to the 5th? Yeah, I'm trying to, should have, I'm just thinking this is missing a bunch of stuff and this is, they're both missing stuff, so I can either add it for all. Yeah, we'll see if I made a mistake after we start. X cubed times what is 2x to the 5th?
2x squared.
Okay. line this up here, minus 2x squared. So I'm gonna line it up where the 2x squared would go, which is kind of in here. And then I'll subtract. So I get negative x cubed positive 2x squared plus 2. And then I ask x cubed times what is negative 2x cubed, or negative x cubed? Minus 1. And again, with doing this work for end behavior, the remainder doesn't matter. It just goes to 0 as x goes to infinity. So, can you read the rest of that flow chart after it says do polynomial long division? What does it say that I should do at this point? Yeah, so it says find the horizontal or oblique asymptotes. What would I say to that? Are there any horizontal or oblique asymptotes? No. So by definition, asymptotes are straight lines. They're vertical, they're horizontal, or they're linear, linear equations, y equals mx plus b sort of things. We know this is not linear because it has a square in it. It's a quadratic. But it doesn't mean it's useless. It describes end behavior. What's the end behavior of y equals 2x squared minus 1? That's like this. So the end behavior, we know of that function, the end behavior is going to be something like this, because it's a parabola. So it's not that it's useless because it's not an asymptote. It's just, it gives you other information, such as the two ends are both increasing. Piggy?
So if you just like, so if you saw like if the difference between the degree is more than 2, then you just not do all the work.
Yeah, you could have probably stopped after the first term, because after the first term, you know if it's a cubic, if it's a square, and you know if the first term is positive or negative. If it's negative, you know they both go down. It's a quadratic. But you do need to know the end behavior when you're graphing it. So you will need to know like what the degree is, and then whether it's positive or negative, because that'll tell you the end behavior. So the next step is graphing it. So you'll need to go a little further than just know asymptotes. Right. Now we're going to be analyzing this graph, which means essentially graphing it. So first thing, consider the domain. What is the domain of this function? Good. Is it going to be a whole or a vertical asymptote? Whole, the issue, the domain issue cancels out. Vertical asymptote, it doesn't. Yeah, it's a vertical asymptote. Vertical asymptote. So let's start graphing it. So I have a vertical asymptote at x equals 0. So, boop, 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 boop. And the way we denote these is with dotted or dashed lines. In my mind, that indicates it's not actually a part of the graph, but it helps guide the graph. Okay, let's look for x and y intercepts. The x-intercept occurs when y equals 0. What's our x-intercept? Yeah, there's none. There is nothing you can plug in for x to make this true. If you write 0 equals 1 over x squared, nope. There's nothing you can plug in there. 1 over 0 is not 0. So you might think, oh, well, this is a bummer. There's no information. But actually, this is a lot of information. This means it does not cross the x-axis. So you don't want to touch the x-axis. How about the y-intercept? The y-intercept occurs when x is 0. Yeah, that's no good. So there's none. So no X or Y intercepts. Take a look at your flow chart. Does it have a horizontal or oblique asymptote? And if it does, what's the equation? Yep, it has horizontal at y equals 0. You should be on the green part. I'm going to draw that in, y equals 0. Okay, pick points to analyze behavior in between the asymptotes and intercepts. So I'm going to have to pick some points. So x and y, let's pick some negative numbers. If x is -2, what is y? 1/4. -1, what is y? I'm going to do -1/2. What is y? Or, heck yeah. You gotta flip it over, because you do -1/2 squared is +1/4, 1/1/4 is 4. So we can kind of get a sense of it's gonna hug this asymptote, and then it's gonna go up and hug that asymptote. And then over here, x, y, how about if x is +1/2? What's y? Yep. It's going to kind of be like a mirror. Because you're just doing the same thing. It'll just end up being the same y value. It's like a little volcano. So unfortunately, with this process, you will have to actually pick points. Like we'll get to the point where we'll get to pick a minimal number of points because we'll get really good. But at this point, we'll have to pick a little more points. Okay, so we have one vertical asymptote, which means we should have 2 branches because it cuts it into 2 different branches. Any questions?
So is there anything else that's like next to each other, or just like across each other, just by the equation?
Well, it has y-axis symmetry, so you could have known that if you tested for y-axis symmetry. Or you could pick either or. Other questions? All right, and we can also look at it as a transformation of a function. So this is a transformation of the function we just graphed, but the -2 near the x moves it 2 to the 1. 2 right, and what does the +1 do? 1 up. And when you're transforming a rational function, you want to move the asymptotes. That's going to help you out the most. So I'm going to take that function I just graphed, that one right here, and I'm going to move it 2 to the right, the pinky one, 2 to the right, 1, 2, and I'm going to move the green one 1 up, and I'm going to draw the volcano. Name of natural disasters. And then do we remember the graph for y equals 1/x? That was one when we did our function lesson. Y equals 1/x. Oh, nice little representation. Now I'm going to like that. Like that. And then we had an asymptote here, asymptote here. We didn't know anything about asymptotes at that point. I probably said the word, and who did that function presentation?
I think that was the one that none of us wanted.
No.
Okay.
No, I don't think she did it. She did. Which one did that?
Did I do it? I might have done it. Either way, here it is.
Oh, no, we did. We did Q.
Okay.
I did Q. We did Q.
And that is 1 over x. And we can move that up, down, left, right, flip it over. What else? All right, there's your assignment. Excellent critical thinking today.